Hi friends, we are in our week 8 and the topic is operation research, and today's subject is inventory management. We had 3 lectures earlier, starting from introduction, and then finally we came to inventory management. So, why this topic is so important? Because every vendor who is dealing with some product, he wants to know, or any organization who has got a store, they want to know what should be the inventory, and if that inventory they work upon, what is the that is based on the consumption rate of those inventory items. If that is given, then how much we should have inventory in the store, so that there are no losses associated with the spare that is available, spare not available. That means we are not having spare when we needed them. Okay, so those losses, how we work, or if we have excess inventory, what is the cost involved in maintaining undue inventory. This is, I mean, telling you in common word. All these things, they have one specific technical parameter. If we so inventory theory, and that leads to the field of inventory management, is inherent part of any organization, including industrial, healthcare, energy, space, aviation, etc. Probably many of you may be knowing there is a Japanese concept called just in time. Just in time means with any item that you need, it will be available just in time. You don't have to wait for it. Okay, and that can be the best situation. Just in time can happen by having over storage also, but that is not a correct place, because you are investing a lot of money in having stored items. So if the item is available to you on the shop floor or in the plant just in time, that is a very good situation, and this is a very important Japanese paradigm that everyone is trying to follow. Now, but then complex mega systems experiences more with and without having a rational and optimized inventory for following reasons: special requirement for critical items and complex supply processes, transportation system, hazard potential, clearance and requirements. A lot of administrative procedures are involved in procurement of these articles, and then there are transportation system. There are special transportation systems that are required to transport the mega components. So that is where it becomes little challenging to have product just in time. Then quality level requirements. I mean, if you open the box and you find it's not meeting the quality, but Japanese were able to do it because they are known for having quality actually. Storage and maintenance of site inventory and constraint. I mean, these are the some cost involved in storing the items more than the required one. And then of course, if you keep it in inventory, then aging management is a issue. Like many organizations, they have special items and they maintain in the store for a longer time, and when those items are taken out for installation in the plant, we find they failed immediately after putting into. First you assume they were very special equipment, like a special rectifier unit, and that was lying in the store because they didn't want to delay the project for last 2 years. And when it was opened and connected with the plant circuit, it found it failed. So aging is a very important aspect in the inventory management. And funding constraints, of course, from available bottom line, you have to have your your profit also. So that this any gap area here in the bullets, they will be taking away or chipping away your profit, that is bottom line of the business. So the objective function is, even though this technique is mostly used for maximization of profit, the metrics could be maximization of safety, risk and security, software reliability, system reliability or availability maximization, quality assurance in healthcare. Okay. Total value of inventory in the United States, you can see the impact how is more than $1 trillion. This is more than $4,000 each for every man, woman and child in the country. The cost associated with the storing inventory is also very large, perhaps a quarter of the value of the inventory. So these are the indicative the observations, and that's why everybody is trying to work on inventory management. Major elements of inventory management for adoption is formulation of an objective function. These are steps actually. Determining the scope of the problem, the development of a policy statement, and that includes objectives also, and then identification of constraint, assumption and postulations, and this is where the randomness comes into the things. Development of mathematical algorithm, data collection and analysis and optimization of inventory management system. But as I mentioned in the previous slide, there are challenges associated with the specialized items and special plants which are risk critical or safety critical, and at the same time they have to meet high demand on let's say a power plant. It has to deliver power also. If it remains shut down for let's say even one day for an item, the losses are in crores actually, which takes time at all. Now there are two, that's why this technology of inventory management has evolved into deterministic and probabilistic, okay, because there are uncertainty associated with the procedure. So inventory in the store, let us say deterministic and probabilistic. Deterministic will give you point value and then optimized model. This will be discussing, but from this how should we can extract a probabilistic model, that also we will discuss here. Probabilistic random variables are used, probabilistic distributions are used, optimized model results median value with uncertainty bounds, you know. So it helps in taking decisions. Let us see cost matrix. What is the cost matrix? Setup cost. Setup cost means if I want to produce some item, I will have to set up machineries for placing the order or demand, okay, and this is one of the very important factor, that is called, it is a constant for a given industry. And then unit cost. What is the unit cost of the item that the supplier expect? So and then holding cost. Suppose if he is holding it in a storage for longer time, there are costs associated, and one is holding and other pole is shortage cost. If he is not able to supply, he will hold it for continuous delivery, but then the storage cost is very high. So shortage cost. So you should not face this situation. Shortage means loss to the supplier who has. So somewhere the optimization can occur between this, and then there are some additional metrics in IT, that is inventory theory. Here IT means inventory theory. Okay. Salvage value of the leftover items or liability of the. Now some items are not being sold and they are lying in inventory, that is called salvage cost, you know, or they are aging. So the recovery of these items, that is, they are very expensive. Discount rate, blocked capital in maintaining the inventory. That so if I keep items in the store for a longer time, this cost might become prohibitive actually, even though you did it for continuous supply, but then this has alternate. So if I blocked my money, that means I cannot use that money somewhere else. It is called blocked money actually. continuous review. Continuous review monitoring instantaneous value of the inventory status. So this is a very good method, and I think this only we might discuss, but assumption here is the per unit delivery over a period of time is constant. So periodic review. So continuous review and periodic review. Normally this is considered better monitoring of inventory of a fixed interval. So lead time, time between placement of the order and replenishment of the inventory. So this is called lead time. Why we are discussing this? This one of many of these factors will form part of our modeling. Optimized time or optimized quantity that we should have in the stores. So this is an economic order model. That means only economics is playing a role. Money, saving money for any product that we are dealing in inventory in stores. And here we have something that is Q is the inventory quantity that we are able to hold. Then it will deplete at the rate of Q minus dt. Okay, and finally this is the period Q by D. Okay, so this is a batch size. Q is the batch size. Inventory depletion rate is Q minus D, that is rate, gradient of this line we have here. The cost considerations are setup cost, we have discussed. Before we place a order, whether it is a machine, we have to set up, we have to place some, we have to procure some items for that setting. So it has got a cost. Holding cost per unit time. For every unit, what is the year? What is the H? Is the holding cost, and C is the unit cost producing or purchasing a unit inventory. Unit cost producing or purchasing a unit. So C is the unit cost, and Q by D defines this time. So this is a time domain and this is inventory domain actually. Now there are some observations here. Formulation of mathematical model. The inventory modeling is a complex task given the synergy of interaction of parameters. However, a good starting point could be with certain assumption and use of deterministic approach. Okay, and then it can be translated into a probabilistic approach. Assumption could be many. I think I can go on discussing because every parameter is a variable parameter. So probabilistic approach through the capturing random variables is expected to provide a more effective solution. This can easily be done by embracing. So what I am doing is I am discussing here the deterministic model, but in that equation, if I assign a distribution, and that means I am assigning the uncertainty associated with the parameter. So my output also will be the model or result with uncertainty, and that can be done using this Monte Carlo simulation that we have here. So if I have developed a model, it is a question of writing a program associating a random variable. Let's say if you use log normal distribution, error factor and median value. These two you have to, median value is like mean rate, whatever you assume, and then the upper bound. Whatever upper bound is there, the error factor is the ratio of upper bound to the median value. That's how we get the error factor in log normal distribution. Okay, so now we are formulating the mathematics of inventory management or optimization of minimum. Now the setup cost, we know it is S, so it is a constant. Okay, then the ordering or production cost per unit can be given as setup cost is one factor, and then per unit cost is one thing, and the total inventory or batch that it comprises for. So this becomes the ordering production cost can be okay, and then we know that mean inventory is Q by 2. Q means why? It was Q on that scale, and average will be, if I take mean inventory, if I take Q by 2, this could be a median value considering a log normal distribution. Then the cost of the holding inventory. Holding inventory will become means what? H and Q into Q by 2. Okay, this becomes the total cost. So because average inventory is this and holding cost is this per inventory, so it becomes the total holding cost. We already discussed that cycle length is Q by D. Okay, previous slide we have seen that the cycle length, this is Q by D. Okay. So here we use this parameter Q by D, and cycle length is this one. So now holding cost per cycle can be given as, now it is per cycle, HQ by 2 into H will give Q will get HQ square by 2D, because this multiplied by this you will get this holding cost per cycle is as follows. And now we got the holding cost. Okay. Now having obtained the holding cost per cycle, the S represents the setup cost, okay, and QC is the unit cost. Okay. Then total inventory cost is, again we will have this one, that is setup cost plus inventory total cost. Okay. Because unit inventory cost is this one, and Q is the inventory, and HQ is we got from the previous this thing, HQ square by 2D. So for the total cost is how much? This one. Okay. T is equal to S plus upon Q by D, because we are giving it for one cycle. Okay. So per cycle. So T is equal to total cost is equal to, if you solve this ds, this ds is not differentiation, d into Si, Q square plus UC 1. Now if for getting the optimized value for T or for this one inventory, for a value of Q, that is Q square, that is minimize the time T, can be obtained by setting the first derivative. So we find out the derivative, dt by Q is equal to ds by Q square plus H by 2 is equal to 0. So we set this equation, and finally we get the optimum inventory size is equal to square root of 2 ds by Q. Q is the optimum inventory minimized cost. Now having obtained the this cost, now if I use a Monte Carlo simulation, I can get the optimum uncertainty. So for that I will need the distribution of D, distribution of S, and distribution of H, and I will get the uncertainty associated with the Q also, and that is where I can combine one simple program we have to write, number of iteration we have to assign the distribution, and we can obtain the uncertainty associated with the Q, which will be more beneficial for us to take a decision. We will be having the upper bound, lower bound, both these things, and median value also. So inventory theory is one of the integral module in operational research. Inventory theory is a critical component of supply chain management. Nowadays we talk about the supply chain management, but in many places the inventory theory or inventory management is appearing there, and it plays the central role there actually. We have discussed only deterministic part, however there is a guidance on probabilistic modeling also. And EOQ model has extensive application in, there are many other models, but this model, it focuses on the saving, cost saving. It is used extensively in operation research.